Hi everyone, my name is Jerry and I'm an AI student at the University of Edinburgh, which city you can see on the slide. I want to thank all of you for your interest in this work, and I want to thank the organizers for making NeuroMONSTERs so much interesting this year. Our group would like to share some results of our work on self-organizing neural network models on behavior control. First of all, I want to outline some problems underlying this research, the main questions I want to answer. Then I want to introduce some principles in our models that we get inspiration from. Next, I want to introduce some modeling framework I'm using, the diamond model, and how it is useful in modeling self-organization in brain. Then I want to show our experiments and evaluations to apply this model to different many robots. Finally, I want to show some promising perspective of further research and the relevance to combining it with other popular learning methods. Great. So I first want to start by asking a question. How is the brain different from deep neural networks? We know that in the brain, there are so many neurons and they have so many connectivities. But in deep neural networks, you can only backpropagate in one way. Therefore, we believe a model should have this upstream and downstream connectivities. And maybe they should have this feedback loop and also feed-forward loop. Maybe they should also have some inner circles in it. We know that not all of those neurons in the brain are directly connected to the muscles or the sensor organs, but most of them are actually doing this incept looping, where they are actually just only supporting each other neurons to keep this functionality stable to some sense. Also, we believe a model should model this perception in the context of previous actions. So the sensor values you have taken is not only used to calculate the next state values, next action values, but also it is used to analyze for the previous action values. Also, we believe the model should give this spontaneous activity, or meaning that action should occur at any level of the brain. And this action should have this real interaction and reaction in real time, should be adaptive and flexible. Also, we think this compositionality of higher level and lower level actions or intentions are very interesting. And we believe this compositionality of different functions of different modules could be very interesting to deploy in these brain models. So this is a well-known example of hierarchy in the virtual context of the brain. So what we're going to see is we can see some clear layer structures. And it could be very interesting if we cut off the lower half of this structure and see if this internal connection still exists between these internal layers. For example, these red lines. This should also exist in the model. And maybe the surface environment is not from this lower half, but from this blue line showed here. It could be the new surface environment in this new architecture. I want to introduce the basic control module we are using, which is the formulation of the sensory motor loop. So we start by having this X0 input from the environment. And then we have a controller module, a controller matrix to calculate this next, the action value, Y0. And then the action conducted in the real world, W, and it outputs a new true state, X0 hat. And then also in our head, we could have an imaginary world, which is shown here, the model matrix, also called feed-forward model in the neural network. After this feed-forward model, we have this predicted next state, X1 hat. And the error here is the prediction error calculated by the difference from the predicted next state and the real next state. So we use this error to update this model matrix M. So in our imaginary world, we can know about the world dynamics or how the world should interact with our system. Then another principle was proposed by Professor Rafter, and he says, what if we use different errors for this learning? So considering we start from this next state value X0 hat, and we reverse back the time, and we go back the time, we calculate this predicted or reconstructed action value. So this is the action value of the previous state considering the current state. And therefore, we can construct this error which is from this reconstructed current state and the true current state. And this error is called reconstructed error. We calculate from the next state, from the next time state. And this is used to update the controller metric C here. What this error means is a sense of sensitivity of the system. So any little change in the current state input can result into a large effect in the output, in the actions or the next state. That means our system is gradually keeping it into a critical regime between stability and instability. If this error is kept small enough, then the behaviors could emerge quite rapidly. So we want to combine this principle along with those other principles. And how is this possible? So we're gonna achieve this by another 3 principles we're gonna show. First is this surface relativity. The surface relativity, as seen in this rubber hand experiment, you have the participant have this real hand underneath the table, and they put a rubber hand on top of the table, and you first you stroke it. After the participant developed the same feelings, it used a knife to cut into it, and the participant got shocked. Therefore, we believe this participant's brain has developed its neuroplasticity and have this development, and this development help it to perceive the rubber hand as a surface environment to the brain input. But in our model, we model the first module which directly interacts with the environment as the surface environment. But for the inner layers, we put the previous layer as the surface environment to take into consideration. Also, on this principle of locality, which means the weights in each module are adapted based on the local information in the sensory motor loop from the feedback of its own loop. So it does not get any global updates or global information. We want to keep an estimate of this predictive information inside these own layers. Another principle also very relevant is this duality principle, which simply means sensing and acting are computationally complementary. As seen in this graph, so if we want to achieve something, our brain could come up with a detailed plan, and then we know all the steps and carry out the steps with our body, and we make a change to the world. But also we can have the same feeling if we only take these word changes into our perception and understand these changes. Our brain could also know how our actions result into some kind of changes in the world. So therefore, we see this loop from this action to the sensor, and from the sensor to this action or to these brain controllers. Here is a demo. We put this homeokinesis or basic control module into real actions. The snake robot is put into a bottle, and the goal is for the snake to get out of the bottle. We see a lot of possibilities for this movement. And also here is a real example of how these different behaviors emerge. And the robot is quite flexible because our algorithms takes this, because the homeokinesis algorithms take the body, environment, and the feedback loop into account. And we stress on this embodiment effect of this robot morphology and how robot can learn itself, its own dynamics, and also this dynamics of the world. The question is, can we do more? So we have this one layered structure here, which is similar to what I explained previously. But then we also have this virtual input and virtual output that we get directly from this first layer. And we use this as the input to the second layer. So we stacked all these layers together into a heretical model. And we want to show this model is very effective in our self-organization model in the brain. Why is this the case? So first of all, we can think of the 3 principles that I'm stressing. First is the surface principle. Every layer is only taking the previous layer as its surface environment. It do not directly interact with other layers. And also on this locality principle, which basically means the error updates are only based on local information. So we update this M matrix, model matrix, and C matrix, controller matrix, by these arrows directions. We see those input neurons, which denoted as X, and these output neurons, Y. They have many connections through this circuit. We believe that these directions is this kind of different ways to sending all those messages. And it is very useful to model it this way. We believe this can achieve the self-organization within these neuron levels. Every neuron are connected either by these upstream arrows or downstream arrows. But also on different view, we see this organization through these different layers. For example, if the third layer want to convey some important messages, how does it do it? It uses this Y2 input, which layer 3 looping on its own generates some virtual actions and then want to use Y2 to commit to the word. But then the second layer goes into effect. Second layer can agree or disagree with this environment. It could enhance this signal or like decrease, minimize this signal. So maybe the second layer acts as a blocker, doesn't want the third layer's message to commit to the word. And the second layer's message actually take much more importance and conveying into the word. So it's actually performing different layers actions, and it has some self-organization through these layers. We do not know this functionality of these layers or modules, but we can self-organize this in a way that is flexible, adjustable. Also, we see in this model, another interesting thing is it forms this inner circuit, which we can see the blue shaded area. This circuit just looping on its own. It doesn't need any interactions from the environment or the input output. So these are very similar to the brain. So a lot of supporting cells, they do not actually connect to the muscles as I previously talked. They just checking in this loop if everyone is okay, if the system is functionable. And another example is when you're sleeping. We know like a lot of neurons are actually activated and they just checking the system and they do not like giving any information or messages. This loop could really well model that case. And this could be very versatile, as I will show in future. This is an example of this multi-layered diamond model into action. We gave the four-wheeled robot an exploration task in this uneven terrain, and we see it covered a large part of this area. The third layer module actually covered much more than the first two layers. And now here is put into real robot experiment. I'll just fast forward a bit, and you can see the robot is actually generating a lot of different behaviors. So it's moving straight, turning around, and moving in curves. And also, interestingly, the robot covered a large area of this environment, as we showed previously. Also, on this interaction of this robot morphology and the environment, we see here, when the robot bumps into the wall, the robot can quickly find an adjustable way to change its behaviors quickly and adapt to the new environment, and then make different behaviors and just do not get stuck in one place for a very long time. So for discussion, we were actually thinking about do the higher levels represent longer time scales, meaning that in our model, the higher levels have more reasoning and planning in it because of the example I gave about the second layer could do its own functionalities. And the messages could be a combination of all these layers, or it could be an amplification of only one layer. So they could self-organize into different representations. But we want to know how this learning rate can change these layers, because we do not exactly know this. We do not really think that our model have the capacity to model the superiority. We don't think the higher layer could have more superiority than the lower level. Maybe they could be the same level, or maybe just talking to each other, and they could change their superiority. So we want to say, what if we change the learning rate? Maybe we decrease the learning rate and like this information to send out to a longer time scale, and your action you're doing is considered in a long time dynamics. So if we change the learning rate of the first layer, will the first layer be the higher level layers, or is there some effects between them? Also, in this heretical model construction, we see a lot of redundancies. So as the example I gave of the inner circuit, they have a lot of variations of it. And this, because these do not directly affect this environment, therefore we have this diversity or redundancy in this model. But we also believe in our brain, we have the same, some kind of redundancies. Because sometimes what we do not reveal what we think, and what we think is not really what we do. So, and also finally, we believe this homokinesis is, since homokinesis and this diamond model is an additional principle we want to use with this self-organization in the brain. We want to say, can we incorporate other learning methods such as reinforcement learning? So maybe reinforcement learning can be realized conveniently in the architecture in form of this guided self-organization, meaning that the higher level representing some abstraction of this information could be regulated by some reward. And we're very interested to see if this high level can be regulated, can be reinforced by some reward, and how those lower level actions can put into effect. Or on different thought is that after we have generated all kind of behaviors, we can do a reinforcement learning on top of these primitive behaviors and generate more meaningful behaviors altogether. To conclude my talk, I would like to say our model have achieved some kind of supervision from this top layer. And also we utilize this noise in a way that we using this prediction error, we using construction error, we try to see if this interaction between this environment in this feedback sensory motor loop can really help the robot to learn stuff by itself autonomously. Or so we do not pre-program it any rules or stuff. We just let the robot learn by itself and adjust to the environment, which seems very natural to the robot and very makes sense of the world. That's what we're trying to do. Also, we believe our model can have this emergence of complex behaviors because of this heretical model construction. Finally, I want to revisit the question I asked about the deep neural network and diamond model difference. So our model achieved these neuroscience principles, duality, locality, and service relativity. We think these are very relevant to brain, and our model should have this should stand on these unified principles. And also, we believe the self-organization not only occurs on these neurons interactions, but also they occur on these modules that as the previous example I showed about visual cortex. We should do something like that. If some part of it is not functioning well, how are the other parts? Do they generate new connections? Do they have some new modules emerging, or how they should self-organize through those connections? Finally, we believe every system, or in this implementation level, we believe from all these robot experiments, we think the behavior generated should be in the context of the physical world about the environment. So the robot should not only know about what happens to the world, but also should know what it is capable of, what can it make sense of the world, and how it should change its own dynamic, know about its own dynamics, and to adjust quickly to the world, to be more flexible according to those information it get.
Different levels of your hierarchical network. Now, how does this prediction error come together with actual tasks, or that you try to include into this model? Because from my understanding, like such a model, if it was just about predicting the right, so for example in this sensory motor loop, just minimizing the prediction error, you could imagine a state where the robot is in, let's say, a completely dark room, not moving, which would make the prediction error 0 because nothing is changing. So how do you incorporate this intrinsic motivation of actually solving a certain task?
Thank you for the question. So our model is not exact. So this is not like a reinforcement model. This is not like a reinforcement learning where you have a specific reward and you do specific task and you train it for them. And this is like a development stage of the, for example, like how this infants get some actions generated. So we believe our model is kind of like a generative model. So every layer could have its own intentions, and it do not convey directly to the word, but they just talk to each model, which also have other intentions or actions. And then they combine these intentions into a way, into a sensible way, and finally interact with the word using this first level. And also on this, another question you asked about the prediction error. So here, we do not really use the model matrix update. So we do not really use this prediction error for update. So we do not really want to know a perfect word model. But we are more interested in this controller model, which is how to make this robot more controllable and also more sensitive to the environment. Say if, as the example I gave you about the robot bumping into the wall. So the robot want to be predictive, but also want to be controllable, saying the robot want to change different behaviors, not doing this one actions, but also your action should not be just doing randomly. You should like keep it predictive. So if you can predict this action quite well, then you can change to another behavior and do stuff. But you cannot predict it. It might be to predict it. So in the real implementation, we set this model matrix to a unit matrix and we set the learning rate to 0. But for this controller matrix, we updated it accordingly. Yeah, so we actually want to make the robot more controllable. If that answer to your question.
Yes, thank you.
Thank you.
Great. I think, and that's all we've got time for, but thanks again for a great talk, Jerry, and for asking the question, Fabian.